Okay, so in this example, an airplane is flying at an airspeed of 500 miles per hour at a heading of 330 degrees. A wind of 70 miles per hour is blowing the plane in the direction of north 45 degrees east. Find the ground speed and direction of the plane. In other words, the pilot's instruments are measuring 500 miles per hour, a heading of 330 degrees, but that wind is going to blow it off course a little bit. So what is its true course and direction from the ground? Okay, so we're going to draw the picture here and use what we've learned so far to set everything up symbolically and figure it out. So, okay, so let me draw a couple of arrows here. Okay, let's draw the airplane arrow. The airplane is flying, the vector for really it's a velocity vector for the airplane. I'll write that down in a second. It's flying at an airspeed of 500 miles per hour at a heading of 330 degrees. Ooh, how do I represent that? So I go from a heading clockwise from the north, right? So go 330 degrees clockwise from the north. I end up in the northwest quadrant, don't I? Okay. I didn't want that to be black. Well, I can change it later. Okay. So we'll make 30 degrees left over. Yeah, it's close enough. And let me change the color on that. Change it to blue. So this blue vector is the velocity vector for the airplane. Okay, what should the length then, based on what we just got done talking about, what should the length of that vector be? 500, good. The length of the vector is its speed. Okay, so the length of the vector is its speed, so the length of this guy is 500 miles per hour, which sounds strange to say the length is 500 miles per hour, but that's how we model it. And then there's a 70 mile per hour wind blowing in the direction of north 45 degrees east. So that's a bearing as opposed to a heading. Where would that put me? It would split the northeast quadrant, right? Now here's the thing. Here's how we model it. We're going to take the wind vector, which I'll represent as W, and it's really a velocity vector for the wind. And the way it affects the velocity vector for the airplane, we add them together. They add vectorially. And remember, the way we add vectors is, well, I'm going to put the tail of W on the tip of V, and I'm going to head in a direction of what I think is 45 degrees from there, headed in the northeast direction. But it's got to be 70, a length of 70, right? So it's going to be a lot shorter. Now, is it going to pass that? I don't think so. Probably not. Sometimes it's hard to tell, though. Okay, so I'm going to call that my wind vector. I'm going to make it red. And then the plane's true velocity vector measured from the ground will be what we call the resultant vector, which is the sum of the two vectors. So V plus W equals the plane's true velocity as seen from the ground. Oh, the plane's true velocity vector, and we'll say from the ground. From a stationary point on the ground, right? So what do we do to find that? And by the way, we call this the resultant vector when we add two vectors together, in case you hear that word, resultant. Okay, but I didn't really complete the thought here, right? So how do we add V, the vector in blue, plus the vector in red, W? We connect the tail of v, the vector in blue, to the tip of the vector in red. And that's going to be your resultant vector, v plus w. So really this 500 right here is the magnitude of v. This 70 right here is the magnitude of w. Okay. So visually, does everybody understand what's going on? It should make sense, right? Because that wind vector should give the plane a slight tailwind, but it's not straight on, right? So that resultant vector should be a little longer. I mean, in other words, the plane should gain a little bit of speed, because it's not totally, the wind vector is not totally going against the plane. It's going a little bit with it, but it shouldn't be all that much. So that picture looks reasonable. And then it should shift it off course more towards the north. So and again, I didn't scale the 70 and the 500 appropriately, but I think that'll be good enough. I just eyeballed it. Okay, so now we have to get the symbolism here. We have to figure out symbolically what v and w are to grab a hold of that resultant vector and know what those values numerically are. In other words, if we want the speed, the real speed, we're going to need to take the magnitude of v plus w. And if we want the true direction, we're going to need that direction angle for v plus w, which means we need v and w in symbols so we can add. Okay, well, we can do that because earlier we talked about this formula. If you have a vector v and all you know is its magnitude and direction angle, you can get its component form by taking the magnitude times the cosine of theta to get the horizontal component, the magnitude of v times the cosine of theta to get the horizontal component, the magnitude times the sine of theta to get the vertical component. That's exactly what we're going to do here on both vectors, v and w. Okay, so what would v be in symbols? What's its magnitude? 500. And then the first component goes 500, the magnitude times the cosine of theta. What's theta? We have to be careful here, you guys. We have to measure it mathematically, not using a heading. So we know that for the vector in blue, that angle measured clockwise from the north is 330 degrees, right? But what is it mathematically measured from the east, from the positive x-axis? Well, what's the leftover angle? 30, and then the northeast quadrant takes up 90, so 120? So 120, does everybody see that? 30 plus 90. Okay. So we're good there. So the horizontal component 500 cosine 120, vertical component 500 sine 120. And then if you can, and we can, get exact numbers just for practice. The reference angle for 120 is 60. It's in the second quadrant. So what's the cosine of 120? Except it's negative. And what's the sine of 120 in the second? So it's in the second quadrant. Reference angle 60. Positive root 3 over 2. So if you multiply 500 times negative a half, what do you get? Negative 250, which means you're still in the second quadrant. 500 times root 3 over 2? 250 root 3. Okay, now v. I mean, not v, w. What was the magnitude of w? 70. Now so it's going to be 70 cosine something, 70 sine of something. Well, that something is the direction angle. It's a little harder to tell when you don't put the initial point at the origin, but when you in other words, when you don't put the tail at the origin, but when you put the tail of a copy of W at the origin, hopefully it becomes obvious that this angle is what? 45 degrees. Which, since we can simplify it, because both cosine 45 and sine 45 are both what? Root 2 over 2, so what would that be times 70? 35 root 2, so both times, 35 root 2. Okay, so we've got V, we've got W. Let's go ahead and find the resultant vector, V plus W. And symbolically, we can do it now. So what do you get for the horizontal component? Just add corresponding components. So what do you get? Negative 250. That's from V, right? Plus what? 35 rad 2. Then from the vertical components, what do you get? 250 rad 3 plus the 35 radical 2 for, well, this one, right? Now, a lot of times on the test, I just have you go this far because there's only so much you can do on a test, and these problems are kind of long. But to answer the question, we have to go further. We have to find the magnitude. But you guys are in pre-calculus, so I'm going to trust that you guys can do this. Now, it's a matter of plugging it in the calculator is all you have to do, okay? Symbolically, then, I'll write it down for you. The true velocity, or the true speed, then. So I'll say the true speed of the airplane as measured from the ground, you'd get by taking the magnitude of this thing. It's the magnitude of V plus W. And then that's going to be a big old square root. And what do you do then? You take that horizontal component, square it underneath the square root, add it to that guy squared. So negative 250 plus 35 rad 2. Whoops. My 5 and my radical got combined. The whole thing squared plus the second component squared. 250 radical 3 plus 35 radical 2. The whole thing squared. Oftentimes in the calculator, I just do the radicand first, and then in the next step, I take the square root. Just because it gets a little messy to have it all, but you can do it however you want. So I'm just going to give you the answer here. Let me scroll down and get it. You can verify this for me if you want, but it's going to be approximately 522.5. And what units are we in? Is it a distance that the magnitude represents? What did we write right here? Miles per hour. Approximately 522 miles per hour, which makes sense with our picture, right? It looks like from our picture we should get a little bit of a tailwind. So we should be going a little faster than 500 miles per hour. That does make sense. Now, you can see that from the component, well, you can see that this first component is negative, right? The second component is positive. So my picture is right as far as which quadrant the resultant vector is in it. It's in the second quadrant. Now, when we find the direction angle, using tangent inverse, it's going to spit out an angle in the fourth quadrant. Then you have to adjust. Basically, all you have to do is add that angle it spits out to 180 to get the angle in that second quadrant. So I'm gonna again, I'll set it up symbolically, but I'll let you guys verify this on your own. The tangent of theta then is, well, we're just going to take this component, set it equal to this component over this component. So 250 radical 3 plus 35 rad 2, that's your B, divided by negative 250 plus 35 radical 2, that's your A. And if you, okay, so you have to take the tangent inverse, then add to 180. So you would take, let's give this quantity a name. What do you want to call it? Okay, I'm feeling duh. It's been a long night. Duh. So we're going to take 180 plus the tangent inverse of duh. I'm not referring to you guys. I'm referring to me. I'm getting tired. Okay, you can call it anything you want. Call it A, whatever you want. And then that turns out then to equal theta. And if you run that through your calculator, that'll be approximately equal to 112.6. Now, the only thing is we were given the direction that the plane is headed in as a heading, right? So could you convert 112.6 to a heading? So measure clockwise from your perspective, clockwise from the north that way. Well, so back to this is where the picture comes in. If you know that this angle to the vector in green, that's our resultant vector, is 112.6, then what we need is, for heading, is that angle, right? So how are you going to get it? Well, couldn't you take the leftover angle here? What's that going to be? Subtract out 90 from the northeast quadrant. 22.6. And then what could you do with that? So, in other words, going clockwise from the north, we're only off one full revolution by 22.6 degrees. So couldn't you subtract that from 360? Yeah, okay. So as a heading, we could say that it's approximately, it turned out to be I guess I could do that in my head if I were awake. 337.4 degrees.